Thank you very much, the organizer of the conference, in special the chair, Professor Adalat Pana, and Dr. Ali Sarurkha, who helped me in some matters. Thank you very much. Thank you for those who are attending this conference and sharing their ideas. Thank you very much. My talk concerns topological frameworks on notozofic graphs, which a new approach, adjacency-based approach. This is a joint paper with Dr. Ganana Chandra and Lalitam Pigai. In a notozofic graph, each edge and vertex can have a degree of truth, falsehood, and indeterminacy. Well, by incorporating notozofic topology into adjacency relation, we aim to represent the relationship between vertices and uncertainty, allowing us to model situations where the connection between vertices are not absolute, but are instead fuzzy or uncertain. This topology is induced by the adjacency relationship between vertices, where the connection between vertices is represented as a notozofic set with truth, falsehood, and indeterminacy values. This is, of course, this is different from fuzzy graph, classical graph, and intuitionist graph because of the degrees of truth, falsehood, and indeterminacy. Make it more precise. We have the definition of a notozofic graph is a graph where the edges are represented by notozofic sets. Each edge between two vertices Vi and Vj is associated with a notozofic set denoted by N, and we have TE, FE, and IE represent TE, the degree to which the edge is present, the truth, and FE represent the degree to which the edge is absent, falsehood, and IE represents the degree of uncertainty or indeterminacy about the edge. A notozofic vertex set is a collection of vertices where each vertex V is represented by a notozofic set, and T of V represent the degree of truth, F of V represent degree of falsehood, and I of V represent the degree of indeterminacy. This definition concerns a notozofic graph based on the vertex set can be formally defined as a tuple. With G, we have V, which is the set of vertices, and E, the set of edges, and T of V, F of V, and I of V represent the truth, falsehood, and indeterminacy values of vertices, respectively. And the same is true for TE, FE, and IE, which is truth, falsehood, and indeterminacy values of the edges, respectively. The notozofic degree of vertex V is denoted by D of V. Again, T of D of V, because it is notozofically defined, is the sum of the truth values of all edges incident to the vertex C, and F of D of V is the sum of the falsehood values of all edges incident to vertex V, and I of dV is the sum of indeterminacy values of all edges incident to vertex V. Then we have the notozofic topology, is a collection of tau of notozofic set that satisfies the following conditions: the empty set we have and the universe of this course, denoted by X, are in tau. The intersection of any finite number of sets in tau is in tau, and the union of any number of sets in tau is in tau. Then we have a notozofic graph. G is equal to VE, which V is the vertex set and E is the edge set. A notozofic adjacency relation is defined between any pair of vertices Vi and Vj. The relationship depends on the truth degree of their adjacency as well as the falsehood and indeterminacy degrees. Specifically, two vertices Vi and Vj are said to be adjacent if the truth value of corresponding edge, DVC E Ig, is high enough. We have this definition for each vertex Vi. Its neighborhood is the set of vertices in Vi to which it is adjacent. In the notosuffix case, this neighborhood may be uncertain or indeterminate. Specifically, if two vertices are adjacent with high certainty, means that TEI is large, then their adjacency is reflected as a part of the open set. If the adjacency relation is uncertain, the indeterminacy I of Eij is significant, and the vertices may still be included in the neighborhood, but with an indeterminate relationship. Well, mathematically, one can formulate it as follows: neighborhood of a vertex Vi for all Vj belonging to vertices, such that T of Ej is greater than or equal to threshold, which is a number, We have an example. Consider a notosuffix graph with vertices V 1, 2, 3, 4, 5, 6, as you can see it. Then the notosuffix edge weights, it means that T and I and F between connected vertices are given as you can see, as this table. Then let the threshold be T greater than or equal to 0.6, and F is lesser than and equal to 0.2. Edges satisfying this condition are included in the adjacency relation. For example, we can see that 1 is adjacent with 2, 3, 5 is with 3, 6, and 6 with 4, 5, and we can also define the neighborhoods N of Vi for each vertex. For example, N of 1 can be the set 2 and 3, and so on, as you can see it. A subset U of V is open if N of Vi is a subset of U for all Vi belonging to U. Take, for example, U of 1, which is 1, 2, 3. We can see the neighborhood of 1 is 2, 3, which is a subset of U1. But N of 2 is 1 and 4, which is not a subset of U1, which is not open. It means that it is not open. And another example is U2. The whole set is vertices, okay? All neighborhoods are within V. This implies it is open. So take, for example, U3, which is 4, 5, 6. And neighborhood of 4 is 2 and 6, but it is not a subset of U3, so it is not open. The same is true with U4, and which is 3 and 5. And we can go on in the same manner, and we can see that so far only empty set and V are confirmed open under the current relationship. Therefore, the notosuffix topology tau on V includes at least the empty set and V. So further open set may be defined if a loser threshold or a relaxed condition is allowed. So if we change this threshold numbers and the condition is relaxed, then maybe we can get more open set or some other relations. So we have obtained the following results. The empty set and the entire vertex set V are always notosuffix open sets in the topology induced by adjacency. The union of any collection of notosuffix open sets is also a notosuffix open set. The intersection of any finite number of notosuffix open sets is also a notosuffix open set. We have the definition of a notosuffix continuous function between two notosuffix topological spaces induced by adjacency is a function that preserves the open sets in the induced notosuffix topology. So we have the theorem. Let's take two notosuffix topological spaces V and W with respective topologies tau of V and tau of W, generated by adjacency relation on the vertex sets of two notosuffix graphs G of V and G of W respectively, and take a map from V to W, call it F, be a notosuffix continuous function. Then for every open set belonging to tau of V, the image F of U is a subset of W is open in tau of V if F is open. It means that it sends open set to open sets. Another result is a function between notosuffix topological spaces induced by adjacency is notosuffixally continuous if the pre-image of any notosuffix open set is open. So they have this remark that these theorems are direct analogs of classical topology adopted by notosuffix settings, where open sets are neighborhoods are determined via adjacency relation and truth indeterminacy falsity threshold. The neighborhoods depend on notosuffix weights, which makes the topological structure more flexible and nuanced. We have this definition, which we have two notosuffix graphs. With adjacency relation R1 and R2 generating topologies T1 and T2. And then we have a bijective function from V1 to V2 is a notosuffix homomorphism if F is notosuffix continuous and then inverse map is notosuffix continuous. So we have this result. We have two notosuffix graphs with adjacency relation R1, R2 generating topologies tau1 and tau2 respectively, and let's have a map from V1 to V2 which is notosuffix homomorphism. Then we can see that V1 tau1 and V2 and tau2 are the same. What we call actually homomorphic. So if you take two maps from V to W and from W to Z are notosuffix continuous function between notosuffix topological spaces generating by adjacency relations, then the composition map from G of G composition with F from V to Z is also notosuffix continuous. Notosuffix graphs offer an ideal modeling tool in such contexts by capturing the degrees of truth, indeterminacy, and falsity in symptom-disease relationships. In a notosuffix graph model for diagnosis and vertices represent either symptoms or diseases, and edges encode the relationships between them with notosuffix values. An edge between a symptom Si and a disease Dj might have a notosuffix weight Tif, where T represents the degree to which Si supports the presence of Dj, I represents the uncertainty or lack of information, F represents the degree to which Si contradicts Dj. By constructing a notosuffix topology on the set of symptoms based on adjacency relations exceeding certain thresholds, we can define neighborhoods that group similar diagnostic patterns. This allows for cluster analysis of symptoms that often occur with uncertain association levels. Patient grouping based on common uncertain clinical presentation. Identification of diagnostic cores, symptom sets that are strongly support certain diseases despite partial indeterminacy. So we have some steps here defining vertices and edges. For example, we have vertices as symptoms: fever F, cough C, fatigue T, shortness of breath S, loss of smell L. Vertices diseases: influenza, COVID-19, pneumonia, allergic bronchitis. We consider on these symptoms as vertices and define a notosuffix adjacency relation based on how frequently symptoms co-occur in cases diagnosed with uncertainty. Step 2, constructed notosuffix graph visual representation. As you can see that, for example, if us have, for example, T and C. Let's see the other slide, the next slide. You can see that we have the symptom pair, for example, if C, which truth value 0.8, for example, indeterminacy 0.1 and falsity 0.1, and so on. So we have this table and we define an adjacency threshold. For example, let's say t greater than 0.6 and f lesser than 0.2 implies strong connection. Using the threshold condition, we define the nosotrophic neighborhoods. As you can see, NF is the set C and T, and neighborhood of C is F and S, and so on. Step 3, constructing a nosotrophic topology. Define a nosotrophic topology on the vertex set FCTSL such that a set U is a subset of V is open if for every symptom V belonging to U, the neighborhood of V is a subset of U. Okay, take example, for example, the set FCT is not open because N of F is CT and CT, the set of CT is a subset of the whole set FCT, and N of C is equal to the set of Fs, which is not a subset of FCT. So only singleton sets like T, C, and full set FCTSL may qualify depending on more refined thresholds. Step 4, interpretation. Topological cluster formed by strongly connected symptoms indicate pattern frequently seen in patients, such as, for example, the set F and C, suggesting flu-like condition. Isolated symptoms like L, loss of smell, indicate high specificity to a condition, COVID, for example, 19, with low shared uncertainty. Using this topology, patients can be grouped based on which symptom neighborhood they exhibit. So application outcome, a patient showing symptom FCT falls within the set FCT cluster and is likely experiencing a flu-like or viral syndrome if the patient also reports loss of smell despite being topologically isolated. The nosotrophic weight between L and COVID-19 can trigger an alert for more specific testing, even if L has weak adjacency. So the conclusion is that this work lays the groundwork for further exploration in nosotrophic topology and its applications. Further research can focus on, for example, investigating continuity and compactness in deeper details, also separation axioms, function space, and so on. So studying homomorphism and homomorphisms between nosotrophic topological graphs, applying these concepts to dynamic or weighted nosotrophic graphs, exploring computational algorithm for real-world data sets in uncertain environments such as social networks, medical diagnostics, and AI-driven decision-making systems. This is our references. We can see that Arblowy and Brumi also worked on nosotrophic graph-based models in medical diagnosis with some other approach. We talked about also this paper of Brumi and Smaradancevic talking about also nosotrophic graph theory and applications, also with other approach. Here, of course, the book is very important, Kandasamy and Smaradanke, Basic Nosotrophic Graph Theory from 2005. And if one wants to know more about fuzzy graphs and hypergraphs, can refer to Morrison and Peng paper from 2000. And these are also, you can see that also Parvati and Kuraman Bigai working the paper intuitionistic fuzzy topological graphs, which they are using in the context of intuitionistic fuzzy topological spaces, you know. Yes, we talked about nosotrophic sets and spaces. I think Smaradanka has also a paper from 1995. Is working with nosotrophic theory, but topological spaces introduced by Salama. Of course, there are different types of nosotrophic topological spaces, but we are using this from Salama and Smaradanka. And Also, his Smartang's paper from 1998 also very important concerning notosufic probability sets and logic. The paper from 2005, a unified field in logic, because it is an extension of dialectics, notosufic logic, and make logic more precise, when studying different phenomena. So that's it. Thank you very much.